In this video, I'll show you how to estimate the elasticity of a demand curve using a log-log linear regression, and also show you how you use that elasticity to compute the optimal price for the demand. We'll do this on the Dominic's data for toilet paper. This data is provided on Dropbox. It contains the week of the observation, the store, whether it was the downtown store or the suburban store, the movement or the number of rolls sold. It's called movement because it's multi-packs, and we'll do this on a rolls or a unit rolls basis. And then we have the price per roll. Now, I'll remind you that these are aggregated across the week, so we don't have individual level data, but we have weekly level data. Here's the data column-wise. We have our store, whether it be 33, if you scroll down, we have the movements for the weeks in store 70. We have the week the sale took place, and then the price and movement of that week in that store. Now, as we discussed in class, the straight linear regression of movement on price does not fit the data very well. However, if we log the two variables, we get the curvature that fits the data better. To log these variables, we use the natural log, which is done by ln price. We'll make another variable heading ln movement. To convert these variables, use the ln function. Again, that's natural log. Don't use log, base 10 log. This is base E. Do the same for movement. And copy to populate the remainder of the column. Okay, now we have our log variables of movement and price, and we want to regress, again, log movement on log price. So to do that, use your data analytics package with regression. Enter for the Y, you'll enter the movement. For the X range, you'll enter price, or log price I should say, because that's your X variable, your independent variable. Include labels here because we've highlighted the column label, the variable label. And I'm going to put the data, or rather the output, here on the same page as indicated in output range. And this is our summary of output. Now we have our standard regression statistics, our R squared 0.34, which is not bad. But the variable that we're really interested in are these standard errors, and these standard errors are quite good given these estimates. Or you could also look at the p-values, which are quite low, suggesting that these estimated coefficients for intercept and log price are statistically significant. The coefficient on log price is the variable of interest for our computation. It suggests a price elasticity of minus 2.6. And as we learned in class, the coefficient is elasticity for the entire demand curve because it's a log-log form. With this, we can compute the optimal price for a firm facing such a demand curve. And again, we use the formula used in class, which is the absolute value of elasticity divided by absolute value of elasticity minus 1 times the marginal cost to the firm, which in this case is the wholesale price of toilet paper, which we stated earlier was 44 cents. So our optimal price is 72 cents. Now bear in mind that we are pricing to the entire market. We are pricing the same price for both stores. But you might say that stores differ depending on whether they're downtown or in the suburbs. In particular, their price elasticities or the price sensitivity of the shoppers who go there are different. This brings up the opportunity to set differential pricing. To compute the optimal differential prices at the two stores, we run the same regression, but do it store-wise. So we'll put the summary output as across both stores, and below it we can do it store by store. So to begin, we run the regression, say on store 33 only. Our x variables now, rather our y variables, are defined by log movement, but only for store 33. Similarly, our x variable rather, as we only have one, is log price, and we bring it to store 33 only. Make sure labels is included. Our output range now will be just below what we had with the two store case. And run. We'll call this summary output store 33 only. I will highlight again the coefficient on log price, which is statistically significant, and if you notice, it is lower in value than across both stores. We can copy the optimal price here, and the optimal price is 80 cents. So the downtown store has a lower price elasticity and therefore a higher optimal price. If we want to run it again, and I will sort this data on store just to bring the store 70 to the top so we can include labels. I run the regression again, but this time for store 70 only, and the X range log price. And our output range, we'll put it down below. And this will be summary output store 70 only. Our coefficients are, again, presented here. We still have statistically significant coefficients. I will highlight the coefficient of log price, indicating the price elasticity. We can copy and paste our optimal pricing formula, and the optimal price is 60 cents. Now you'll notice that pricing across both stores, we priced at 72 cents. When we price differently across the two stores, one by definition will be higher than that previous price and one will be lower. And the reason is we estimate a high price elasticity or high price sensitivity at the downtown store, at store 70. Okay, that concludes this analysis for estimating price elasticity in a log-log demand curve and deducing the optimal price given that demand.